Hi, welcome back. So in this video, we discuss regression models with several explanatory variables. So this is some example of the general notation for a regression model with several explanatory variables. As you can see here, we deal with two of them, x1 and x2. And when it comes to interpretation of the regression output, you have to keep in mind the concept of partial derivative. So imagine that we have a function of several variables, to be more precise, x, y, and z, and partial derivative of f with respect to x shows by how many units f will change if x increases by 1 unit, assuming that y and z are constant. So that's why when we interpret the results of the output of regression model with several variables, we often add this ceteris paribus phrase, which means that we assume that other variables remain unchanged. Like we analyze the effect of each independent variable on the dependent variable separately and assuming that other independent variables keep the same value. So for instance, if we go back to the model we discussed before, beta 1 will be interpreted as partial derivative of y with respect to x1. It will tell you by how many units the dependent variable y will change if x1 increases by 1 unit ceteris paribus, or assuming that the value of x2 remains fixed. Analogously, beta 2 is interpreted as partial derivative of y with respect to x2, and it tells you by how many units the value of the dependent variable y will change if x2 increases by 1 unit ceteris paribus, or assuming that x1 remains the same. For instance, you can consider the following model. So here I analyzed how Gini coefficient, the measure of income inequality, depends on GDP per capita and literacy rate. So basically we can see that if GDP per capita increases by $1, Gini coefficient decreases by 0.00034. Here, Gini is indeed a coefficient, so there are no units for measurement. Again, we assume ceteris paribus, meaning that literacy rate remains the same. Analogously, if literacy rate increases by 1 percentage point, Gini coefficient increases by 0.14 ceteris paribus, or assuming that other variables do not change, their values are fixed. So there is an interesting question, how many independent variables you have to include exactly. For instance, when we think about economic growth, it is affected by capital stock, stock of labor, human capital, institutions such as democracy, quality of legal system, and so on, climate, quality of governance, investment in infrastructure, and so on and so forth. So you can think about many potential determinants of economic growth. And there is a question how many of them you should actually consider, because of course more is better. However, there should be some limit. So here there is no good advice. Basically, you use the rule of thumb, which means that you concentrate on the variables which are frequently discussed in the literature. Also, when it comes to the models with several independent variables, you have to include two more assumptions to the list of assumptions we discussed in the previous lecture. So there should be no exact collinearity and there should be no specification bias. Okay, so now let us discuss what exact collinearity means. Exact collinearity occurs when the sum of two variables composes some constant value. For instance, you can think about proportion of males and females in population. The sum will always be 100. That's why only one variable can serve as the independent variable. Number of hours devoted to sleep, work, and rest. Again, the sum will always give you 24 hours. Only 2 out of 3 variables can be included to the regression model. Dummy for male workers and female workers. Again, the sum of these variables will always give you 1. So that's why only one dummy variable can be added to the regression model as the independent variable. And of course, we have to distinguish between collinearity and exact collinearity. So linear collinearity is about the exact linear relationship between two variables. However, the independent variables can be correlated, of course, only to some extent, as long as there is no perfect collinearity. So there are several ways through which you can analyze whether the correlation between independent variables is tolerable for you. First of all, you can design the correlation coefficients matrix in GRETL, where you analyze the correlation between several variables. So this is already familiar to you, you know how to calculate it, but actually GRETL has the built-in function. You just have to highlight several variables and click correlation matrix. So here, for instance, we analyze the correlation matrix for natural resources rent, literacy rate, tertiary education rate, and secondary education rate, and capital formation. So here there is quite a high correlation between literacy rate and secondary education, about 0.9. So we can suspect that there should be something close to exact collinearity between those two variables. What else? Yeah, perhaps that's it in this particular case. But, you know, analysis of correlation is always a good idea because it allows you to get some initial idea about the data at the relatively low cost. However, it would be more precise to analyze collinearity. So in this case, you have the test for collinearity diagnosis in GRETL, which works in a very similar manner. And here at the end, you actually get the pairs of variables which are highly correlated. So in this case, you cannot include secondary rate and literacy rate to the same regression for sure, because you are really likely to end up with something close to exact collinearity. So yeah, okay, so that was it when it comes to this video. Thank you so much and see you in the next one.